All right, so we've talked about how we have a list of rules for how to integrate certain types of functions, certain types of basic functions, like the power rule, for example. We know how to integrate x to the fifth power and things like that. And we have a few other specific functions like e to the x that we know how to integrate. But those don't help us once the functions start to get more complicated. Like if you have a product of two functions, we don't have a product rule for integration. So the next two sections, 4.5 and 4.6, we'll be talking about specific techniques that we can use in certain situations to handle more complicated kinds of functions. So 4.5 is what we'll talk about in this video, which we might call integration by substitution, or the substitution method for integration. So before we say exactly what that is, let's review the chain rule for derivatives. So this is just review. So if I wanted to take the derivative of a function like x squared plus 5 to the 9th power, this is derivatives now, not integrals. I'm taking the derivative. I have an outside function of the 9th power, so we bring that 9 down first and decrease the exponent by 1 to get an 8 up there. The inside stays the same. And then I have to multiply by the inside's derivative, which is 2x. So if I simplify this, 9 times 2 gives me 18. Let's put this x in front. 18x times x squared plus 5 to the 8th. Okay, so that's just the chain rule. That's an application of the chain rule. Now let's think about how we would integrate this function. If I happen to come across the integral of this exact function, 18x times x squared plus 5 to the 8th power dx. Let's just worry about indefinite integrals for now, so no numbers. That means we're just looking for antiderivatives. Well, the antiderivative of a function is a function for which this is the derivative. Well, we just saw this is the derivative of x squared plus 5 to the 9th. So the antiderivative of this would be x squared plus 5 to the 9th power. But since it's the general antiderivative, I have to put the plus c after that. All right. So the question that we want to address with the substitution method is, what if I had seen an integral like this just originally? I didn't happen to do the exact derivative right beforehand and recognize that I had the answer sitting in front of me. So if I just saw this from scratch, the idea of the substitution method is, how do I recognize what function did it come from as the derivative? Okay. So let me do a similar one. Okay, so let's just do an example of a very basic substitution problem, just to illustrate how it works. All right, so suppose I wanted to integrate x, or let's say 2x times x squared plus 8 to the 5th power. The idea of substitution is we want to make a change of variable. Okay, so I'm going to make up a new variable. The default, the one that most textbooks use for this, is u. You can use other variables if you want. W, so it's a good backup, whatever. But u. And what I'm doing is I want to look at this integral and find a part of it that I would benefit from replacing. And here's what I mean by that. So in this case, I've got this fifth power applied to this relatively complicated expression, x squared plus 8 raised to the fifth power. So I would really like it if instead of x squared plus 8, I just had a single variable there. So like if I had u to the fifth. So my guess for the substitution, and sometimes it takes repeated guesses and just kind of experimenting to find the right substitution, but my guess would be u equals x squared plus 8. Okay, so I'm going to say u is equal to x squared plus 8. So then my goal is to turn this entire integral into an integral involving just the variable u. And so any x's that appear need to eventually disappear before I have made a successful substitution. That includes the dx. So right after I make my choice of what u is going to be, I need to then figure out what is du equal to. Du is going to be the differential of this expression. So that means two things. Take the derivative, which would be 2x, and then since it's a differential, I always have to multiply this by dx. Alright, so now my integral, I want to say it's equal to some integral that only involves u. So here's the way I approach it. My first goal is I need to get rid of the dx and replace it with a du. But it's not just rewriting dx as du, it's making a trade. Du is the same thing as dx times 2x. So I go up here and I ask, I've got dx of course, it's right there. I also need 2x. And in this case I happen to have 2x right there. So what I'm going to do is take this 2x and this dx and trade them in for a du. So I'm going to get a du by using these two things here. So those are gone. I've gotten rid of those, now I have du. Then I look at whatever's left, x squared plus 8 to the fifth, and I need to rewrite that in terms of u. Well, in this case, u is exactly x squared plus 8. So this is u to the fifth power. Right? Yeah. So now I have a new integral, and it's a simple one. It's a simple power function, u to the fifth power du. So my power rule would give me 1/6 times u to the sixth power plus a constant c. So now we've integrated. We've gotten rid of the integral and the du. That's gone. Now we have our answer. Except our answer is not written in terms of the correct variable, because our actual problem was an x problem. So whatever my final function is, it should be in terms of x. So now what I need to do is replace u with x squared plus 8. So let me rewrite this. So this now is equal, let me just put it here, to 1/6 u gets replaced by this expression, x squared plus 8 to the sixth power plus c. So this is my final answer. Right? So that's the idea of the substitution method. It's about finding some part of your integral that you can replace with a new variable so that the entire integral becomes a more simple function with that new variable. Right? This was a tailor-made case, though. Everything worked out perfectly. In general, like I said, making substitutions can be tricky. It takes some trial and error, and it kind of requires you to get a feel for certain rules of thumb for how to make a good choice. So let's do another example that's not quite so simple. Okay, so integral of x squared divided by x cubed plus 7. Alright, so again, this is not one of our basic functions. We can't simplify our way out of this because I can't divide by the two things separately. When you've got addition or subtraction in the denominator, it makes things messier. It can't be simplified usually. So what I want to do is make a choice for u. And here are the two rules of thumb. One, like we said on the previous example, we're looking for some piece, some expression in our integral that we would really benefit from replacing with a single variable. So what that means is we're kind of looking for an inside function. Think about the chain rule. We're looking for some function that's inside of another function. Okay, so in this case, that would be x cubed plus 7 because it's inside the denominator here. Right? So let's put x cubed plus 7 as u. Then we calculate what is du. Well, derivative would be 3x squared times dx. And this is kind of the key step. I want to look at that du and ask, do I have enough stuff to work with to get du from what I have? Okay. Well, if this denominator is u, the only other thing I have to work with is this x squared on the top. I've got an x squared that I need. I need to have an x squared to come up with du. So I've got dx, I've got x squared. I've got two of my ingredients. I don't have the 3, but that's okay because the 3 is a constant multiplier. I could take this equation and say, well, du is the same thing as 3x squared dx. That means x squared dx, the stuff I actually have here, is the same thing as 1/3 du. So, let me box that off to the side here. My integral would be, now we try to change it over now. Again, first try to get du. Well, I need to trade in x squared and dx to get my du. X squared and dx are going to give me a 1/3, which let's put out front here, and a du. And then I don't have anything left on top, so I'm left with a 1 there. Alright, so I traded in x squared and dx. That gave me the 1/3 and the du. Then remaining, I have x cubed plus 7 in the denominator. That gets replaced with a u. So my integral becomes 1/3 times the integral of 1 over u du. That's one of our basic functions. The antiderivative of that is 1/3 ln of u plus c, the natural log of u. And then our final step then is, after we've integrated, we have an answer in terms of our variable u. We want our answer to be in terms of the original variable. So this last step is simple. I just go back and replace u with whatever it was, x cubed plus 7 in this case. Okay, so our answer is this. 1/3 times the natural log of x cubed plus 7, then plus our constant c. And by the way, before we do more of these, you can always check your answers. If you want to check that you did everything correctly, once you get to this last step, if you take the derivative of this, the c will disappear. But if you take the derivative of this function, I should get something that is equivalent to our original problem, the original function here. Okay, so let me stop before we go into more examples. Let me just formally write the two rules of thumb here. So how to determine u, how to pick u. I need to say u is equal to something. So two things to look for. The first rule of thumb is look for an inside function. So that's an expression that's inside of some other part of the formula. So it could be inside of a parentheses raised to a power. It could be inside of like a square root or a cube root or something like that. It could be inside of a denominator. It could be inside the exponent of an exponential function. Could be inside of some other function. So that's one thing to look for. There may be multiple possibilities, even if you're looking for inside functions. There may be a couple things that you could think of as inside functions. But once you choose one, once you make that choice, then the next step is think about what is du. If you make that u, what is du equal to? And then that's going to be the determining step, whether or not your substitution is going to work or not, or be easy or not. And so the next thing to look for is you need most of its derivative. So like on the previous one, this was the example, x cubed plus 8, whatever it was, I can't remember the number, but x cubed plus 8, if that was my u, du is 3x squared dx. So if I'm going to make this substitution work, I need to have most of this stuff. So I'll always have the dx, that's not a problem. But I needed that x squared. The 3 I didn't need because it's a constant part. But you essentially need to have whatever the variable part is to get your du. So you compute du, I need to have whatever variable stuff is there. Sometimes there's ways to manipulate things to account for missing parts of it, but it can get difficult or impossible in some cases. So you don't need, I need most of the derivative. Most here means other than constant multipliers. Because like we had before, in the last example, I didn't have the 3. I had the x squared, which is what I really needed. So the 3 is negotiable. I can just divide that to the other side and say, I can't get exactly du, but I can get 1/3 du. 1/3 du was x squared dx. So I can deal with constants. I can deal with missing the constants, but I need to have the variable part. Okay, so when you're making your choice, you're looking for inside functions whose derivative is also present as a multiplier, other than maybe some constant multiple. We're having the wrong constant multiple. Okay, so let's do another couple here. Suppose we have e to the x to the 4th times 8x cubed dx. Okay, so let's think it through before we write anything down. Here, what are our possible substitutions? Well, 8x cubed, that stuff is not really inside of anything else, so it probably wouldn't help to substitute, but we have an exponent here. We have an exponential function, e to a power, and in that exponent we've got another function, x to the 4th. And by the way, when I write this, just to be clear, it's like there's understood parentheses around that exponent. So e to the power x to the 4th. So the only real inside function here is x to the 4th. And so now you ask the next question, what is its derivative? Well, derivative of x to the 4th is 4x cubed. And so you look at what you've got an x cubed there, so it's going to work. It's probably going to work. So we'll write it out. U equals x to the 4th. That means du is 4x cubed dx. I've got the x cubed, I've got the dx, of course. And now I've actually got a 4 because 8 is 2 times 4. Let me just write that here. 8 is 2 times 4. I've got the 4 I need too. So I can trade those things in. that gives me 4x cubed dx gets traded in for a du. That leaves me with a 2 left over from the 8. This x cubed is gone because I used it to get du, and then e turns into e to the u. So 2 times e to the u. Right, so that's the substitution. Then you still have to integrate after that. So the integral of 2 e to the u, integral of e to the u is just e to the u. So we get 2 e to the u plus c. Now the integral sign's gone. And now we go and undo our substitution. This is 2 times e to the x to the 4th plus c. All right. Okay. Next point I want to make. Suppose I had integral of square root of 3x plus 7 dx. Here, the choice is fairly obvious, I would say. We've got a square root, and inside that square root is 3x plus 7. So clearly the only inside function here is 3x plus 7. Now the type of function it is special. It's just a linear function. All it is a mx plus b, a linear expression. There's no x squared, there's no x to a power, just something times x plus a number. So this is a linear expression, and it's true that we can always substitute a linear expression successfully. We can always make the substitution to get rid of that linear expression. So u is equal to x plus 7, then du is 3, derivative of this is 3, times dx. And so when you're substituting a linear expression, the derivative is always just the number, and numbers are negotiable. If I don't have the number I need, I can divide it out and make it work. So 1/3 du is dx. I always have dx. So I can always make this work for linear situations. So we get the integral of dx turns into 1/3 du. And then square root of this is just square root of u. That's a power function, so we can integrate that. That's u to the 1/2. So we integrate u to the 1/2 by adding 1 to the exponent. That gives us u to the 3/2 power. Divided by 3/2 is the same as multiplying by 2/3. So we get 2/9. And now let's undo our substitution. U is 3x plus 7. And it's raised to the 3/2 power. Okay. So we'll do more examples. There's something else I want to talk about though before we do more. This is conceptually, as far as concepts and definitions goes, this is a fairly short section. It's a fairly short topic. The difficulty with substitution is practice. You just have to practice these, look at more examples, and just try to get used to picking the appropriate expression for you. So practice the problems on homework 12 from 4.5. But we'll do some more. But the next thing I want to talk about, so far all the examples we've done have been indefinite. So they're just antiderivative problems. Now let's do some examples that are definite integrals, meaning now we have x values involved. So suppose, right, we want to do the integral from 0 to 2 of x times x squared plus 1 cubed dx. Alright, so we have a definite integral problem. So it's an integral, but now we've got the numbers on it. But if I ignore the numbers, this clearly is similar to the problems we've been doing. It's a substitution problem. We've got an inside function that we need to get rid of. With definite examples with numbers, there are basically two different approaches I can use. So let me show you both ways of doing it. One way is I just ignore the numbers at first. So I look at the indefinite version of this problem. I'd say u is equal to x squared plus 1. That's my inside function here. Its derivative du would be 2x dx. I check, do I have the x I need? Yes, I do. I don't have the 2, so I say 1/2 du is the same thing as x dx. I divide both sides by the 2. So now I'd say this is the integral of, I trade the x dx in for a 1/2 du. Then I've got x squared plus 1, so that's u to the 3rd power. Now we integrate that. That's 1/2 times 1/4 u to the 4th plus c. That's 1/8. Now let's undo our substitutions. That's x squared plus 1 to the 4th plus c. And so I finished the problem without numbers. Now I've got an answer for that, so I have the antiderivative. So now I can go back to the original problem and plug in my values to this antiderivative. Okay, so now I'd be almost done, but now I have to go back. Let me keep that there, but now I'd say, okay, I have my antiderivative, which is 1/8 x squared plus 1 to the 4th. I don't need the plus c, because I'm going to be plugging in numbers, and when I subtract, the plus c will just disappear. So I don't need the plus c. Now I plug in 2 to this. That's 2 squared plus 1 to the 4th minus 1/8. Now I plug in 0. That's 0 squared plus 1 to the 4th. And I think this, let's double check this. You work this out, you should get 78. But you notice, so that is the answer. Unless I made a mistake, but that's the answer. But there's a different way I can approach this. And the reason I might want to do it this second way is, once you get to this last step, after I've found this function, I have to go back and plug in values. Excuse me. When I plug in those values, the function that I am dealing with is sort of complicated. So I get lots of calculations I have to do all at once here. All right, so instead, what I can do, I know the substitution I want to use here, so that's why I didn't erase it. I'm going to use it again. What I can do is, when I make my substitution, should have kept this. This was 1/2 u to the 3rd du. When I make my substitution, I can convert the numbers. So 0 and 2 here, those are x values. Since it's dx here, these are x values. Well, now if this is u, du, if this is a du integral, if I'm going to put numbers on here, they need to be u values. So what I want to do is say, when x equals 2, what does u equal? Well, when x is 2, that's at the top here, u is x squared plus 1. So if I plug in 2 to that, 2 squared plus 1, that's 5. So this 2 here turns into a 5 on the u integral. And when x is 0, u is 0 squared plus 1, that's 1. So 0 turns into 1 at the bottom of the integral. Right? So if I do it this way, once I completely turned everything over into u, including the two numbers, they're now u values, I can forget that x ever existed. So now I would say, okay, let's integrate this. That's 1/2 times 1/4 u to the 4th. And now I'm just going to plug in 5 and 1 for u. So that's a much simpler calculation now. It's essentially the same calculation, but I've already gotten rid of some of the calculations here when I made these conversions. So now it's just 1/8 times 5 to the 4th minus 1/8 times 1 to the 4th, which will come back and give me the same 78 if I calculate that. Okay, with a definite integral problem, when you have numbers, your final answer is just a number. So there's two ways you can get it. You can either go through, find the answer in terms of x, which is its own substitution problem, just like we were doing in the earlier examples, but then you have to go back and plug in the x values to calculate. Or when you make the substitution to get a u integral, you can just convert those numbers into the corresponding numbers for u. And if you do that and you plug these in for u down here, you'll get the same answer, but it's kind of breaking down the calculations into easier to digest steps. I'm not doing it all at once at the end. All right, so both these two methods are equivalent. If you do them correctly, they'll give you the correct answer, either one of them. So just do it the way that makes more sense to you. It's easier for you. All right, let's do another example of a definite integral. Most of the time, I personally prefer the second method just because it's shorter and easier to write down in a sequence of steps. So let's do another one. All right, so see how this goes. Integral of 3 over x plus 5 squared from 0 to 4. Okay, so we look at this, and there's a lot going on down here in the denominator. So we want to first make a substitution. So we want to make u equal something. This time there's sort of two possible choices that you might gravitate towards. You could, like we did on an earlier problem, you could take the entire denominator and treat that as an inside function. So let me write that down. If you're using ink when you're taking notes, don't write this down. If I did this, if I said u is equal to x plus 5 squared, then the next step would be, what is du? And that's going to be a fairly complicated thing. I mean, this is a chain rule, so to have, well, not that bad. We'd do 2 times x plus 5 times our inside derivative would be 1 times dx. Okay, so I could do that, but I don't have that. If I don't have that beyond, all I have to work with is this denominator. I made that whole denominator my u, so there's not really anything left to make this out of. And by the way, if I say I need to have x plus 5 to make this work, that x plus 5 in this case, since it's being multiplied here, would have to be on the top of the fraction. It couldn't be in the denominator. So I couldn't use an x plus 5 from the denominator to make this du. Okay, so what the point I'm trying to make here is, don't be overly ambitious when you're making your choice of u. If you make u too complicated, its derivative will be more complicated and therefore harder to find in your integral. So that was too much. So instead, you look at, well, if I don't want to make the entire denominator my inside function, x plus 5 is also an inside function. And the good news is it's linear. It's just x plus a number. So the derivative of that is dx. I've got dx. I always have dx to work with. So this substitution will work. So let's convert it. First thing is, in this case, dx equals du, so I just replace it. And now I've got 3 on top still. X plus 5 is u. So in the denominator I have u squared. And that's going to be something I can integrate. But let's also fix the bounds. So when x equals 4, u equals 4 plus 5, which would be 9. So my top number becomes 9. When x equals 0, u equals 0 plus 5, so my bottom number turns into 5. Yeah. So one minor note of caution here. When you are changing these bounds, it's possible that when I plug the top x value in and find the u value, and when I plug the bottom x value in and find the u value, I have to do a one-to-one change. This 4 turns into this 9. So since 4 was on the top, 9's on the top. Now it could happen that when I make the change, the new integral has a bigger number on the bottom than on the top. And that's kind of unusual from the examples we looked at so far. But you have to make sure to keep the positions equivalent. Whatever 4 turns into, that goes on top, even if it's smaller than what ends up on the bottom. Okay. If you mix it up, it changes the sign of your answer. If it's positive, it becomes negative, and vice versa. Okay, so we have our new numbers. So now we can forget that x ever existed. Let me give myself more space in that. So our new integral, let me rewrite it, 3 over u squared. Let me remind you, the integral of that is not ln of u squared. Ln only shows up in the specific situation where you just have the single variable as the denominator. So this is 3u to the minus 2. That's a power function. So that would give us, when I add 1 to the exponent, it becomes negative 1. Negative 2 plus 1 is negative 1. And now I have to divide by negative 1. So that would be 3 over minus 1 is negative 3. So before I plug the numbers in, this is negative 3 over u. So I'm going to plug in 9 and plug in 5. So negative 3 over 9 minus negative 3 over 5. So that becomes 3/5 minus 1/3. Let me. I can forget that x ever existed. This becomes 3/5 minus 1/3, which is 9/15 minus 5/15, which is 4/15. Right. So that's our answer. If you did it the other way, where you first found the answer with u, so you integrated this, and you put x plus 5 back in place of u, then you have to plug in x equals 4 and x equals 0. You'll get the same answer if you do it correctly. Okay, so I want to do one more example to make one last point. And this last point is substitution. The substitution method helps us with a lot of more complicated functions. It doesn't help us with everything. So we can make up complicated functions where none of our basic rules apply. Substitution can't be accomplished. So we're stuck with our current methods. But I want to make the point that sometimes we can make a substitution, but it's not as straightforward as the previous examples. So let me just show you a relatively simple one, but still a relevant one. Suppose I wanted to integrate x times the square root of x plus 3 dx. We'll just keep it indefinite. I don't want numbers to obscure the point here. All right, so you look at this, and I can't simplify my way out of this to get a basic function, but there is an inside function. X plus 3 is an inside function, and the good news is x plus 3 is a linear function, so my substitution shouldn't be too difficult. U equals x plus 3. So then du would be dx, 1 times dx. So now let's try to substitute. Well, dx is du, so we got that. Inside my square root, I've got u, so I have square root of u. But I'm left with this extra x that didn't get used. So I could write this, and it's common for people to write this, x times square root of u du. If I write that, it's fine as I'm trying to figure things out, but I can't leave it like this. So in an integral, I can't have a mixture of variables. I can't change some of the x's to u and leave other x's behind. To have something that makes full sense, everything has to be converted to u's. So I need to do something about this x. And here's the rule of thumb. Here's the principle. I can only use the du equation once. I can't get more than one du's out of it. I don't want more than one du's. That'd be bad. So any other conversions have to come from this equation. And so in this case, I can say, how do I get rid of this x? Well, x would be the same thing as u minus 3. So I can say this x, let me just erase it, x turns into the quantity u minus 3. So parentheses u minus 3 times square root of u. All right, so I've successfully made my substitution. Now we have to answer the question, does it help us? Does it help us to integrate? And the answer is yes, it does in this situation. So I was able to convert to a different variable. Just because I do that doesn't mean that my new integral is easier. It might still be the same level of difficulty. I don't know. But in this case it is better because in the original function the addition or the complexity was inside of my square root. And that's keeping me from distributing, basically. I could distribute, but it would make something more complicated, and that'd be bad. Now the complexity, the addition, in this case subtraction, is outside the square root. So I can distribute the square root of u, like so. I get u square root of u minus 3 square root of u. Both of these they're now separated by a minus sign, by subtraction. Both of these are now simple functions that I can integrate. They might not look like it just yet, but they are. U square root of u, that's u to the 1/2. So if I multiply u times u to the 1/2, that's u to the 3/2. I'm adding the exponents on my u's. And then I have minus 3 times u to the 1/2. These are just power functions now, individual power functions. I can integrate those. So u to the 3/2 becomes u to the, I add 1, that gives me 5/2. And then I multiply by the reciprocal of that, that's 2/5. Minus u to the 3/2. I multiply by 2/3. I already have a 3 though. So 3 times 2/3 The 3's cancel and I just get 2. Okay, so I was able to integrate. Now the only remaining step is to plug back in x plus 3. So my final answer, let me erase the middle part here. Let me squeeze it down here because I want to summarize at the end. So u is x plus 3. 2/5 times x plus 3 to the 5 over 2 minus 2 times x plus 3 to the 3 over 2 plus c. So there's my final answer. So let me just say a couple things about this example, and that's the end of this section. So first off, remember this was an indefinite integral, no numbers, so my final answer has to be a function, and in that case my final answer needs to have the same variable that I started with, x. So I have to undo my substitution at the very end. If I had numbers there, I could have converted the numbers and then plugged them into my u function at this stage. So that's one thing. The other thing is just to reiterate the main point of this example, and that is sometimes making the substitution requires you to make more subtle use of this u equation, so I can solve it for x. If I can solve it for x, then that allows me to replace x with an expression of u everywhere it occurs. And so when it's a linear expression you're substituting, that's usually doable. I mean, that's always doable. Then the question is, when I make that when I successfully convert everything to u's, does it get me to a better place than where I started? And a lot of times it will, because what you started with usually has complicated stuff inside of another function, and when I do this, that frequently transfers the complexity outside the complicated function. So then you're able to do some more algebra to simplify it, like we did here. We distributed it. Okay, but again, substitution's tricky. It's our first difficult technique for integration. The only way to get good at substitution is to practice more and more examples. So look at the assigned problems on the online homework. You can cycle through some related problems, like do it once and then replace it with an alternate version to try again. But do practice. We won't be looking at any that are too difficult, but they can get tricky, and sometimes it just takes trial and error to get to the correct substitution. And again, one more time, just because we have this technique doesn't mean it works all the time. There are integrals we can make up where even if I'm able to make a substitution, the substitution didn't really help me. So there are many techniques out there for integration. We'll talk about one other one in the next video. But even with those, there are functions that just can't be integrated, or they can't be integrated with elementary functions like we have here. Right, so next time we will do 4.6, and that's the other half of homework 12. All right, so I'll stop there.